So, you have already listened to my first two lectures and got some idea about phase equilibrium and also the phi energy formulation. Today, we are going to do some recap of these and then move on to derive phase rule. So, I just wanted to show you that I showed you this picture last time, that two shields are moving in a ice water mixture, and they are trying to understand what are the factors which can be used to describe the two phase single component system. It is a single component system because it contains water, and there are two phases because you have ice and water, liquid water. So, therefore, can we describe this thing in terms of measurable thermodynamical parameters? The questions of this kind of thing will be answered in today's class. But before I do that, just I would like to recap you few of the things. You know, thermodynamically any system is defined to be at equilibrium when there are three equilibrium things are satisfied. One is a mechanical equilibrium, second one is your chemical equilibrium, and third one is the thermal equilibrium. So, mechanical equilibrium analogy I have discussed you with matchbox concept. Thermal equilibrium means in the system there will be no temperature gradient, and chemical equilibrium means the reaction rates of the forward and backward reactions will be same. So, there will be no net change of the reaction. So, when all of these three equilibrium, that is mechanical, chemical and thermal, are satisfied, we call the system to be at thermodynamical equilibrium. And as you know, all the phase diagrams are calculated based on thermodynamical equilibrium. So, therefore, we must learn the thermodynamics of equilibrium first. So, in doing that, first we like to do thermodynamics of single component systems like water, the one which I showed you just now. Water is a single component system with molecule containing two hydrogen atom and one oxygen atom with the formula of H2O, but it can have two or three phases. See, if two phases coexist together or three phases like water, liquid water, ice and vapor coexist together, how can we describe a system? So, let us do that first. Well, to do that we have to first get back to phi energy expression, that is the expression I have written at the top. Phi energy is here the Gibbs phi energy, and Gibbs phi energy is defined as G as a function of temperature is equal to H as a function of temperature minus T S T. So, where H is nothing but the enthalpy or the heat content, and S is the entropy of the system. And we know that by knowing the Cp, we can calculate both the enthalpy and the entropy. Just by integrating over Cp in T reference to T, we can get enthalpy, and by Cp by T integrating over T reference to T to actual any temperature, we can get entropy. So, by plugging in these two, we can get an idea about the phi energy, and I showed you in the last class that the phi energy curve for such a kind of system will look like this. We plot G versus temperature. Okay. So, phi energy of a solid will be looking like this. This is Gs, and phi energy of a liquid will be looking like this, Gl, right. And the cross section of these two will be giving us the melting temperature. Temperature at which both solid and liquid can coexist is defined by this point. Why does this curve have such a kind of slope? It is because of entropy. If you carefully look at, this is a negative slope, so slope of this curve as a function of temperature is basically minus entropy, and entropy is a positive quantity, therefore the slope of this curves are negative. And if we assume the simple equation of Cp is equal to A plus Bt, then we can actually find out by using this mathematical analogy, you can find out what will be the Gt, and that I have done already to you. So, for a single component system, this is the way to describe the equilibrium between solid and liquid, or solid and vapor, or vapor and liquid, anything, so you can do that. We will utilize this diagram when we will describe water phase diagram in maybe another 1 or 2 lectures after this. So now question is this is fine for a single component system because G is nothing but a function of temperature and pressure, and here we have assumed pressure to be constant. If we assume P to be 1 atmospheric pressure, then this is only a function of temperature. But for a alloy or for anything which consisting of more than one element, for the sake of understanding, suppose instead of pure water you have water plus some amount of salt into it, which is the case in sea water or ocean water. In that case this analogy or these derivations will not work. We have to use something else. What is that we have to use? We have to know that how G varies as a function of composition also. That is what we should do. And how we can do that? Let us see how it is possible to do that. So G will be a function of both temperature, pressure and composition of the element. That is what will happen if we consider the free energy of any system consisting of more than one element, and let us suppose there are 2 elements. So therefore there will be 2 composition variables. Here T is the temperature, P is the pressure, Na is the number of molecules of A, Nb is the number of molecules of B. Okay, like water and salt system, Na is the molecules number of moles of water, Nb is the number of moles of salt. For a steel, so containing iron and carbon, Na will be number of molecules of iron, Nb is the number of molecules of carbon. So that means we have to now expand these things in terms of compositions. So if I take a total differential of this, simple maths, if I take a total differential of this, dg is equal to simply df by dt, capital T dt, or this is the differential. Similarly for pressure, similarly for composition. For A and for B. Let me rub up this one also so that you can see clearly. So that means total differential is differentiation of as a function of temperature, pressure, number of moles of A, number of moles of B. And you know that this is can be written like this. I will derive it and show you how it is possible. As a function of temperature and pressure, this is equal to V dP minus S dt. I will just show you right now, and let me keep this one as these, the composition variables as it is. I will not change that right now. So how do I get this? That is very simple. Let us write down here G is equal to H minus Ts. So if I take differential of that, then it becomes dH minus T dds minus S dt. I have just taken total differential, so I have to differentiate everything. So now I know from the first law of thermodynamics, what do I know? From the first law of thermodynamics I know the total energy is conserved. So that means that I can write down from the first law of thermodynamics, I can write down del Q is equal to del E plus del W, which is nothing but del E plus P dV for a gas system, right? This is from the first law of thermodynamics. And what do I know for the second law of thermodynamics? Second law of thermodynamics tells me the definition of entropy, that is equal to ds equal to dq by T. Therefore del Q is nothing but T ds, and this is second law of thermodynamics. Very easy to deal with this kind of equations. Now if I plug in there those things, what I will get? I know H is equal to, I just get back here, H is equal to E plus PV, right. So I can expand dg is equal to dE plus P dV plus V dP. I expand this one fully, dH equal to dE, P dV, P dP. I can expand it very easily. So that becomes minus T dds, T ds minus S dt. So now we can clearly see dE plus P dV is equal to del Q. I can write down from first law dE plus P dV is equal to del Q. So this dE plus P dV become del Q plus V dP minus TdS minus SdT. Is it clear? So now I just go up and write down these things because you can't see from the pattern. So if I just write down here, let me just do it here, I will write it up here, okay, that is better. So it is very clear dg is equal to del q plus VdP minus TdS minus SdT. So dq is again TdS by second law. So I can write TdS plus VdP minus dds plus minus SdT. That means TdS get cancelled. So VdP minus SdT. This is the typical relationship between total differential of phi energy as a function of pressure and temperature, because pressure and temperature are the variables. So that is what I used in this derivation. So I now write it up. You probably have noted down how to derive this expression, and let me get back into the whole derivations of this. So I have seen that this is what is the expression. Now for such a kind of things where G is a function of temperature, pressure and the composition variables, I need to define these terms. But in chemical thermodynamics, these terms are defined as a chemical potentials. What are these? So I define this one del F by del Na equal to mu A. Similarly del F by del in B equal to mu B. So this means that this quantity defines the chemical potential of A, this quantity defines the chemical potential of B. I can write down also chemical potential of A, Similarly this is chemical potential of B. You can define this way these terms. Now what is the meaning of chemical potential? This is something which is very common in thermodynamics but never understood by the students. It always been told in the books that it means if I add a very small amount of A into the solution, into the system, the change of G is what is known as the chemical potential of A. But that is a very vague statement, very vague statement, nobody understands. This means that ability to do work. What does it mean? Okay, let me explain. Suppose if I say you have the potential to become Prime Minister of this country, that means that you have all the qualities to become the Prime Minister of the country. Similarly, chemical potential of A means it has all the qualities to become part of the solution or part of the system, and if they become part of the system, the change of the free energy because of that system is what is known as the chemical potential. So potential means ability to react in basically thermodynamic sense, ability to react in the environment, that is what is known as potential. So if I plug in these values here, I hope you understood this now. If I plug in these values, I get VdP minus SdT plus mu A dNA plus mu B dNB. Okay, this is what I get very simply. Now at constant pressure and temperature, at constant pressure and temperature, I get dG is equal to mu A dNA plus mu B dNB, and G is nothing but then integration of this So I hope you understood this part very clearly. Okay, I write down again at the top so that you can see very clearly. I erase this part. Okay, I erase this also. So I write down that G, when it is composition variables are there, it can be written as mu A Na plus mu B Nb. This is when the temperatures and pressures are constant. That means if I know the composition of any system, then I can actually calculate the free energy system. Obviously, I can calculate free energy system when I know the pressure and temperature, that I have shown you already how it is to be done. What is the quantity you need? You need Cp. If you know the Cp as a function of temperature or pressure, you can calculate G of any pure component, any system where there is no compositional change. But when there is a compositional change, you must need to consider that you have to use this equation to measure the free energy change. If you have to consider temperature and pressure effect, you have to add that part with this, so then it will become a big equation with 4 different variables, Na, Nb and temperature and pressure. That is possible, right? So you got an idea that how to basically incorporate effect of compositions into the system of the thermodynamics to measure the effect of change in the free energy of the system or Gibbs free energy of the system. Now I just wanted to go into little deeper into that so that you can understand it better way. So let me just erase this part and keeping that equation at the top. So what I can do is this, like this. I know that in metallurgy or material science we never deal with number of moles of A and P. We always deal with the mole fractions of any component. Suppose I have 2 components A and B in a system. I know there are Na moles of A and Nb moles of B. Then I can define the mole fraction of A by Xa is like this, Na divided by Na plus Nb. That means the number of moles of A divided by total numbers of moles present. It does not matter whether 2 components present, if there are n number of components present you can do the same thing. So basically this is the way the mole fraction of A is defined. Similarly mole fraction of B is defined like this, number of moles of B divided by total number of moles. So we can actually change this G expression, very simply we can change that. So if I divide by G Na by Nb and call this as a G prime, that means this is per mole basis. This is total free energy, if I divide it by total number of moles it becomes per mole basis. The free energy per mole, I put a prime because to differentiate that, that is equal to mu A Na divided by Na plus Nb plus mu B Nb divided by Na plus Nb. That means it is equal to mu A Xa mu B Xb. Clear? I hope it is understood. So therefore the free energy per mole can be given as mu A chemical potential of A multiplied by the mole fraction of A plus chemical potential of B multiplied by the the mole fraction of B. So this is the generalized expression of free energy change of any system containing 2 components. The why we discuss this thing more frequently in metallurgy is because all our alloys are solutions. Consider steel, consider aluminum alloy, copper alloy, these are all solutions. Because they are solutions, that means there are more than one component present. Solution is nothing but like you add sugar into water, the solution. So this is also a solution, but they are solid solution, not liquid. That is why this kind of analogy must be used. So now it is very clear. So for any pure component, suppose you have only A, so therefore Xb is 0. If B is not present, then Nb is 0. Nb is 0 means Xb is 0. Then G prime is becoming X mu A, because mu Xa is 1, and this is known as mu A 0. By thermodynamics we define it. Similarly, if there is no Xa in the system, Xa becomes 0. So G prime become mu B, and we write down that as a mu B 0. Is it clear? This is what is the way that the chemical potential defined. So whenever we want to talk about chemical potential of pure component, we say we put a 0 here. Whenever we want to discuss pure component, we always write put a superscript 0. But whenever we think it is a chemical potential of a component which contains more than one components, chemical potential of any individual component in a solution rather, we always put mu A. We do not put any superscript sorry. We always put superscript 0 when there is a pure component in a solution. And this can be possible because when you draw the diagrams, it will be clear to you much easily. I have shown already to you in the last class, but I am just defining you this way. Okay, now this is very clear. So just I go to the next few of the slides and show you what are the diagrams I was doing and trying to do that. Let me just go back there. Yes, here. Correct. I'll just tell you that the phi energy of a solution is defined by this curve, defined by this curve. This curve. Phi energy of solution is defined by this curve. So now in this curve we have plotted phi energy per mole, same as G prime, as a function of x. X is nothing but composition. You can write an xb. Okay. Let us suppose xp. xb is the mole fraction of B, and you know that xa plus xb is equal to 1. In such a system, xa plus xb is equal to 1. Very easily you can see. So therefore, if I know xa, I can know xb also very easily. One of the components are required. So now question is this: when I plot this at the pure end, like when A is here, B is here, so for this component xp is 0, for this part xa equal to 0, I get chemical potential of pure A, chemical potential of pure B. And you see I am marked by mu A superscript 0, mu B superscript 0. This is the definition of that. This is what is explained to you right now. So you got an idea of how actually to deal with different kinds of solutions. And now in this diagram again I want to tell you in taking from the last class that this particular curve is basically phi energy of the solution, but this line is phi energy of physical mixture. Physical mixture means they have not mixed atomistically together. So that you can see the nature of the curves are different. For a physical mixture we get a straight line, and but for a solution we get a parabola. Okay, why do we get it? We will explain very soon. But you must see that in comparison to the pure physical mixture, solution is stable much easily or analytically. Why? Because solution has a low energy than the physical mixture if we consider same composition. That is why the solutions are more stable. That is why alloys are easy to make. This is the main reason. That is why if you add salt into water, it forms easily solution. That is why if you add sugar into water or coffee into milk, it gets mixed very easily. This is the main reason. Thermodynamically, this is the reason we always keep that thermodynamically, if we have solutions as compared to physical mixture, because of phi energy change, this gets stabilized. So now I get back to the I'll get back to the derivations of these phi energy curves in the next class. So in a nutshell, I just want to tell you that if you are not able to get ideas very clear, you can either get in touch with the TS, they will explain you, or you can actually read those books I have given you as a reference in the first class. So where actually basic thermodynamical things are discussed. I will not be able to go into details of these thermodynamic derivations in this class because I assume you have already have fair amount of idea about basic thermodynamics or metallurgical thermodynamics, very clear idea. Otherwise, you won't be able to follow many of this stuff. So if you are still not well conversant with these concepts, I suggest you that you also read those two books which I have given to you, or look at literature available on internet so that you can understand very clearly. If these concepts are not clear to you, future lectures will not be also very clear to you, because many of these phase diagram derivations are based on the thermodynamic calculations. The thermodynamics is basically backbone of phase diagrams. That is why this is a prerequisite for this course. So in next class actually I will show you how this curve actually evolves and how can I use this curve to derive equilibrium.